This problem reads, a tiny ball of mass 0.012 kilograms carries a charge of negative 18 microcoulombs. What electric field, magnitude, and direction is needed to cause the ball to float above the ground? So what we have here is that this has a charge of negative 18 microcoulombs, and it has a weight, a mass of 0.012 kilograms, which means it has a weight of roughly 0.12 newtons, and of course that is pointing down. And again, I guess I like to use blue for my force vectors. So its weight is trying to pull it down, and in order to counteract, that means there needs to be a force of the same magnitude pointing up, and that would be the electrostatic force. It sounds a little weird when it says floating above the ground, defying gravity. Well, no, in a sense, it's defying gravity because there is an extra force in it, just like an airplane is above the ground, or a balloon due to its buoyancy is above the ground. In this case, it happens to be an electrostatic force that is acting against gravity. Okay, in any case, let's see what we got. Oh, it says find what electric field is needed, magnitude and direction. Actually, the direction is really easy to figure out. It's a negative charge, and you learned in the book that the electric field, which I will give a different color here, just to figure out which color. There we go, I give it this color here. The electric field points from positive to negative, and that means that a positive charge would go this way because it would be repelled by the positive side and attracted by a negative side, and a negative charge would go in the opposite direction for the same reason. So the way I actually drew the arrow was correct. The electric field has to point down so that this negative charge here would experience a force that is pushing it up, and of course its weight is trying to pull it down, and if it happens to be at rest to begin with, then it will stay at rest. Just going to copy these electric field vectors here. So we have a few more. So the electric field is pointing down here, and we would have a constant electric field here with, yeah, I guess the ground being negative. Let me see if I can. I can't get the same color, purple color here. So here we have a negative all the way through, which produces an electric field that is pointing down, pushing the charge up against gravity. Okay, for that electric field, it would exert a force that equals the electric field times the charge. And because this one is not a spherical electric field, that's why I'm not going to use Coulomb's law that says F equals K Q1 Q2 over R squared, but it's a continuous field as if exerted by a capacitor plate, and the electric field given by a vector, electric force experienced by a very small test charge placed at that spot divided by the charge itself. And so the electric field just is there producing a force, and so F equals Q times E, and that of course is the force that is pointing up. And then of course I have a force that is down, so the weight is pointing down, and that would be negative mass times gravity, of course the negative comes out here, that this arrow pointing down would be at an angle of 270 degrees. Sine of 270 is 0. And of course, in order for it to float, that nothing happens to it, again, it's Newton's second law, which says that the force exerted by the electric field, I'm going to call it E here, plus the weight equals 0 because nothing is happening. Net force is 0, and of course, again, this one is actually negative. Okay, well, then it's just a matter of plugging these in. So charge times electric field plus a negative mg equals 0. One algebra step, electric field equals mass times gravity divided by the charge, and that equals, well, this one is going to be in newtons, mass times acceleration is newtons divided by the charge, so it's going to be Newton coulombs. And then, yeah, you have to plug in these numbers. What did it say? The mass was 0.012 kilograms times 9.8 divided by 18 times 10 to the negative 6. So again, appreciable electric fields, I want to say in the neighborhood of a few thousand newtons per coulomb. Next problem. Electron in a parallel plate capacitor, which says the drawing shows an electron entering the lower left side of a parallel plate capacitor and exiting at the upper right side. The initial speed of the electron is 7 times 10 to the 6 meters per second. That is 7,000 kilometers per second or 4,000 miles per second, so really fast, like in all kinds of electronic instruments. The capacitor is 2.00 centimeters long, very short, a little bit less than an inch, and its plates are separated by 0.150 centimeters, so that's just a little bit over a millimeter. Not to scale apparently, because this one here is about 15 times longer than what this one is high here, so it's not to scale. In any case, assume that the electric field between the plates is uniform everywhere and find its magnitude. So between plates and uniform, and find the magnitude of the electric field. Okay, let's see what's happening in this problem. This one, ooh, does have 2 stars on it. All right. So the electron moves left to right, and if it wasn't for the capacitor plates, because of its inertia, it would keep moving left to right at the constant speed. But of course, there's an electric field, negative down here, positive down here, the arrow's pointing down, and because it's negative, it's repelled by the negative, attracted to the positive, and so on its way to the right, it will deviate from that path and make its way up, and it looks somewhat circular, but you'll see that actually it's a parabola going up. So it's just supposed to clear here. Again, we can write Newton's second law down. So we have some forces here, which would be the electric force. Again, we'll have actually the force exerted by a capacitor plate. And we could say that, well, we have gravity trying to pull it down. If this was actually vertical, it doesn't say so. Let's say it's horizontal and gravity wouldn't play a role. However, even if it was vertical, even if gravity would try to pull the electron down, I will show later when I'm done with the problem that actually the weight of the electron is so small compared to the electric force that it's totally negligible. As I said, I can only show that later. And the reason is that the electric field is relatively high. In order to deviate it, remember, it's really, really fast going through here. So you have to have a huge electric field to actually get it, push it up here. Okay, let's get started. So there is an electric force, and that will produce an acceleration. Of course, Newton's second law is mass times acceleration. The Fe here for a constant electric field would be the charge of the electron, which is simply written as lowercase e, times uppercase E for the electric field, equals mass times acceleration. And of course, one algebra step gives us the acceleration. We actually have two unknowns here. I'm going to write it as such: E times E divided by the mass of the electron. Actually, I should also write a little e right there if it lets me. If it lets me, I will write a little e right there. No, my tablet doesn't let me. There we go. There we go. Squeeze it in there. Okay, that's the acceleration. Okay, acceleration reminds us about, obviously, motion. Something is going on. And it brings us all the way back to kind of the first couple of chapters in this book, chapter 2 and 3, about the kinematic equations, where when you have an acceleration, which we have in the y direction, it's being pushed up here, we have that y equals 1/2 acceleration times t squared. Because of this t squared here, the squared, that's why I said earlier, actually that's a parabola, because that's what the square is. And in the x direction, what we have is velocity in the x direction, the original velocity in the x direction, times time, and because of its inertia, that initial velocity will not change in the x direction, and there is no acceleration in the x direction. So this one here, I'm just going to write it down for just a moment. 1/2 a t squared in the x direction. There is no acceleration in the x direction, so I can just take this off here, and I will. And of course, you see that in the y direction we do have an acceleration, as shown because of the electric field. And we should also have this one here, but again, I'm going to write it down: v0y t times t. So the two equations, the x and the y, way back in the kinematic equations, look the same, but there's no acceleration in the x direction, so I took that term out. And there is no initial velocity in the y direction, so this term actually is not there either. That's why these equations look so abbreviated. And I guess I could say here, because I have my ay right here, I probably should also say that this is the acceleration in the y direction. ay, so I have to squeeze in another index. Okay, I'm going to plug this one in here. So this one is going to be, I'm going to back up just for a moment before I plug it in. I should note which kind of variables I have here. This here's a variable, an unknown. That's an unknown, the electric field. Well, I plug this in here. Okay. That means I still have one unknown right here. Ooh, why is it doing that? Kind of green stuff here. There's a little better. But I don't know the time, so that's an unknown either. But I have the time here, and then everything else is given. So when I substitute this one in there, and this other equation in there, I have eliminated the acceleration, and I have eliminated the time, and the only unknown I will have is the electric field, because everything else is given. Charge of the electron, mass of the electron, the initial speed is in the problem. You can see the x here, 2 centimeters. You can see the y here, 0.15 centimeters. So that's why I do all this algebra. And again, this here comes from that I look at it, well, there was motion involved here, and then there's a deviation here, so there must be something happening with the kinematic equation. That's where it comes from. And of course, there is a force here which produces that acceleration, so that's why I also wrote down Newton's second law. And that's why this problem here has a couple of stars, because you have to think about, well, which equations apply here. And that's why I just tried to explain why there is Newton's second law and the kinematic equations in here. All right, now let me do the algebra. So this one is going to come out to y. Okay, I guess I'm going to keep the green. Y equals 1/2 E times E over the mass of the electron. There it is. Times t squared, but I might as well plug this in, so x over v0x. So x over v0x, parentheses, and that's squared because that's what it said earlier. And then I have an equal, and then I plug in numbers, and if you make the unit analysis, I guess I could do it, the electron, let me try another color here, black I guess, the electron would be in coulombs, the electric field is in Newton per coulombs, the mass is in kilograms, the x here is in meters, but it's squared, and the v0x is in meters per second, but that's squared as well. Alright, so as far as the units are concerned, the coulombs divide out. The newtons here divide out with 1 kilogram meters per second squared, and then there is a meter left here, divided into a meter squared, so actually the unit comes out to meters as it should here for the y. And then, oops, I noticed that actually I have to do algebra on this. This is not what they were asking for. They were actually asking for this one here. Whoops, sorry. Didn't have to do that. Well, that's alright. But actually I would have to solve for E. I missed that part, but here for a moment. So I got involved in the units. But that's no big deal, just a lot of algebra. Let's see, how can I write this best? Okay, there's a 2, and then I'm going to write an ME right there, and then I make myself a long fraction bar. Or maybe I don't need it that long. Divide by E, and then I have a V0x squared here, and I have an x squared here. There we go. And then I have an equal. Then I have my underlined whatever I plug in there, and then I push this out of the way. And actually my unit analysis should have shown that when I put all these units, kilograms, coulombs, meter squared, meter per second squared, that eventually I'm going to come up with newtons per coulombs. And so here at this point, yeah, so actually I don't need to calculate this one over here. And technically I don't need this one either. There we go. So this one here is all given. That's 9.1 times negative 10 to the negative 31. This one here is 1.602 times 10 to the negative 19. This one here is given in the problem as what was it? 7 times 10 to the 6 meters per second, and that has to be squared. And this one here is given as 0.02 meters, and then I notice as I did the algebra, oops, forget one little thing, right? As I did the algebra, there should be a y, and the y is given as 0.0015 meters. Plug in all the numbers, and you come up with the result for the electric field. Oh yeah, and then I wanted to point out why I didn't use gravity, even if it was in the vertical. As I mentioned earlier, maybe I did. You come up with a relatively large electric field, and I can just give it away. It's in the neighborhood of like a few thousand newtons. So let me just use 1,000. I'm not sure what it shows. Why my graphing calculator looks so weird when I get it in here. Oh boy. Okay, so let's assume that you come up with 1,000 newtons. That's actually not too far off. It's a ballpark figure. And I'm sorry, newtons per coulomb for the electric field. And I multiply that with the charge of the electron, which is 1.610 to negative 19. And this here would be the electric force exerted on the electron, and now I compare that to the gravitational force, which is the mass of the electron, 9.1, 10 to the negative 31 kilograms, times the acceleration due to gravity, and notice what happens. That, sure, this number is very small, but it's much, much larger than this number here for the weight of it. It's 10 to the 14 times larger, so even if the deflection plate is in the vertical, the weight of the electron is totally negligible to compare to the electric force. And that's usually true of the electric force. It's much, much larger than the gravitational force. Has its reasons in that the gravitational constant itself is a really small constant, 10 to the negative 11, while the constant that you find in the Coulomb law at 10 to the 9 is relatively large compared to that. However, in our everyday life, of course, gravity is ruling everything, pretty much everything. It seems to be larger than an electric force, but the reason is that most of the things that we encounter in our everyday life are actually electrically neutral, or they have a very tiny charge, so the electric forces are really small because of the really tiny electric charges, or them being neutral, they would be zero. So that's why gravity seems to rule our world, because we always have mass, and mass always exerts a gravitational force. Let me show just one more thing.